All right, so these are kind of the properties of magnetic forces. All right. First of all, the first property is that if I have a magnetic field, that I have a charged particle placed into a magnetic field, then we can say that stationary charges charges that are sitting still, feel no force from a magnet. A moving charge like a charge that has some kind of a velocity, feels a force that's perpendicular to its motion. Here, can I use this symbol for perpendicular? Perpendicular to velocity. Okay. The other thing we know about this is that the force that the moving charge experiences is also perpendicular to the magnetic field. So I'm going to say a moving charge feels a force that's also perpendicular to the magnetic field, okay? And we're using the symbol B for magnetic field just to kind of remind you, this is the symbol we're using for magnets. Magnetic field. Okay? A moving charge feels a force perpendicular to the field, and it also feels a force that's perpendicular to the magnetic field. So perpendicular to the velocity and this, and the size of the force, the size, the magnitude of the force, is also proportional to all of these things. So it's proportional to the charge, Q, proportional to the velocity, V, and it's proportional to the field, B. Okay? We can summarize every single one of these ideas here by saying that if I have a particle and it's moving with some velocity, let's say off in this direction here, and let's say that velocity vector is kind of coming out towards you guys, and we identify that by kind of drawing a little tabletop here or something like this. Okay, if a particle is moving in that direction with some velocity, and let's say that it has a charge that we call positive Q right there, then if I place a magnetic field here, so that the magnetic field is pointing like this, for example, but in the same plane, be like this, the force between these two objects is going to point this way. Use a different color for this. The magnetic force here is going to point up like this. And the symbol we use for this is F sub B. That's magnetic force. Okay. And then if we define the angle between the velocity vector in here to be phi, we can define this in a more general sense. The magnetic force is going to be equal to the charge times the velocity crossed with the magnetic field. This is the cross product right here. To remind you what this ends up being, the cross product states that if I want to find the magnitude of the force, I take Q times the magnitude of the velocity times the magnitude of the magnetic field, B, and you multiply by the sine of the angle between the two of them, the smallest angle between the two of them. These are the two different ways we can describe what the magnetic force looks like. This is sometimes referred to as the Lorentz force in a more general sense when we add the electric field. Every one of these vectors is at a right angle to each other, okay? FB has to be at a right angle to B. Velocity has to be a right angle to B, but then the angle between here and here is phi, okay? So that's why I have a plane. The magnetic force is perpendicular to the plane, and the velocity and the magnetic field are in that plane. That means that the force is perpendicular to V, the force is also perpendicular to B, and then the size is given by these factors right here, as well as the angle between the two of them. Okay? If the charge has no velocity, the V is 0, the force is 0. If the charge is not charged, like a neutral particle, like a neutron, would not feel a force. And if there's no magnetic field, there's no force. In addition, if the angle phi is equal to 0, that means that V is parallel to B, and this leads to 0 force. So you need to have some kind of an angle between the velocity vector and the magnetic field. And that angle can't be 0 or 180, because sine of 0 is 0, sine of 180 is 0. But this in general is going to give you the force. Does that make any sense to you guys? I pulled this little diagram here because it's a little bit clearer way of describing what's going on, since they took a little more time to actually draw this. In fact, let me just put that right there. This is a summary of different possibilities. A charge moving parallel to a magnetic field experiences 0 magnetic force. So whether the charge is moving in the same direction as the field or it's moving anti-parallel to the field, you get 0 force. A charge moving at an angle phi to the magnetic field experiences a force that's qvb sine phi. This is the velocity v. This is the b. You like my drawing more? Okay, thanks. It's always better when you see the drawing develop from nothing than it is when you just see a picture. But for some people, they might want to see this. Notice that v and b are in the same plane in this picture. And so the force F is perpendicular to the plane containing the velocity vector and the magnetic field. Right? F is up. B is this way. Velocity's here, but this is their perpendicular component. A charge moving perpendicular to a magnetic field experiences the maximal force. When the angle between these two is 90 degrees, you get the maximum force right here. Okay. That's in general, that's what the magnetic force is at its core. It's produced by this relationship here. This is, I would call this an empirically determined relationship. This was originally discovered empirically. That means through science, actual science, not through people sitting around thinking about science, but people actually measured how this works. In fact, it's very, very unfortunate that we can't be on campus today. I'm going to show you some of the ways in which this force works with a video, but it would be a lot cooler if we could be on campus and you guys could actually take a magnet and put it near a beam of charged particles and show how this works, right? Unfortunately, we can't do that, but I did find a nice video. I need to be doing this a little bit more as we... this video is up here. Now, how does this work? Does it play inside the... I don't really want to play it inside of here. We're going to go to YouTube for this, actually. We'll watch this on YouTube. This is a little video, and we could do this at our at school too, but let's watch this. Sure. Okay, my mic was off. Okay, so do you have any questions about what we just saw? Yeah. Yeah, yeah. So this is the idea. When I take a magnet that's pointing like this, so that this is the north end and this is the south end, this magnetic field, the simplest way to think about it is that the magnetic field produced by this is pretty much just a straight line like this. Okay? The field is actually loopy, but it's okay to think that near the points, the field is basically straight, right? So he basically brought this next to a beam of particles that were coming kind of out towards us, right? And I'm going to give you guys some notation right here, which is that if I draw a vector that I want to have, this would be a vector that's coming out of the board. Okay, a vector that points out of screen, I guess is what we would say now since we're on screens. Why is it not undoing? What? Okay, just do this. This vector means out of the screen. Okay, and then if I put in a vector with an x, this means into the screen. Does that make sense to you guys? So over here, I'm going to say the velocity vector is coming out. The magnetic field vector is going this way, right? And we can think of that magnetic field as effectively continuing through here. So that the velocity vector is into where you're looking, but the magnetic field is pointing this way. And what I'm going to tell you is that if the particle is positively charged, the force in this case would point... Okay, I need to back up for a second. Does that answer your first question? What was the magnet doing? The magnet is basically just a vector that points this way. Does that help you? Okay. So that's why I was saying that, and this gets into how we actually talk about this. So to determine direction now, we use something that's known as the right-hand rule, okay? And for this, I am going to use this picture because this is extremely difficult to draw. I would much prefer to be showing you like with the video. So this is how we determine the direction, okay? We use the right-hand rule for the direction of the magnetic force on a positive charge in a moving magnetic field, okay? So suppose I have a particle with a velocity that points like this, placed in a magnetic field that points like this, and I want to describe what the direction that the force is going to be is. If I point my fingers in the direction from V to B in my right hand, and I rotate my fingers from V to B, your thumb will point in the direction of the magnetic field. I'll repeat that again. You point the fingers of you can do it yourself right here, looking at the screen, right? Point your fingers kind of out of the board in the direction of the velocity, and then rotate from the velocity vector to the B. And you go through the smallest angle, your thumb should be pointing upwards. Can you guys all verify that you get upwards for that?
Yes.
Okay. Likewise, for the picture below, if you point your fingers along that direction, so kind of like into the screen, and you rotate from V to B, can you see that a particle that was traveling in the opposite direction would experience a force downwards as opposed to upwards? Verify for yourself that you can do this with your hands. And I'm going to give you guys some examples to test with this. Now, let's test it. Let's test our understanding of this with the picture that we just saw from that video. In the video, the velocity was coming outwards. The magnetic field was pointing to the right. If you use the velocity cross with B, so point your fingers... The way to do this, I don't know how you're all looking at your screens, but you'd want to point your fingers kind of... Like what I'm doing is I'm turning around and I'm pointing my fingers out of the screen, okay? And then I rotate my fingers from velocity to B. What direction does your thumb point if you do that? If you go from V to B. Remember that the V vector, the velocity vector is pointing out of the page. The magnetic field vector is pointing to the right. Oh no, what did I just do? I guess that's okay. What do you get for the direction of the force if you do that here? You get up, right? Except that the difference in this case, the reason is he said that you got a downward force was because the particles here were negatively charged particles, right? So if Q, in this case, Q is negative, which means that if you look at the way that this equation works, the Q is right here, right? It actually flicks the direction of the force. So the force would be this way then. So V cross B points up, but you have to flip it because it's negative. And that's the second half of this thing right here. If the charge is negative, the direction of the force is opposite to that given by the right-hand rule. So a negative force, compare this picture to this picture right here, you can see the positive particle feels an upward force, the negative particle feels a downward force, 100% opposite direction. Okay. Does that make sense to you guys? We're going to do some problems to like test out our understanding here. But does the general idea of what the right-hand rule is, does it make sense to you? You have any questions? I know this is pretty complex. And I know that it takes some time to really wrap your head around. So that's why I have these problems that I pulled out from a different textbook. This is from Survey. These are ways that we can test our understanding of this. And I could just draw these myself, but since they're already ready to go, what I want you guys to do is to use the right-hand rule to tell me what's the direction of the force in each one of these pictures right here. So I've got a positive charge. What direction is the magnetic field going in this picture right here? When it says, well, I guess they tell you it's in. It's the way the X's mean in, right? These are our rules, right? I want to say one other thing about this, by the way. The way that I remember these rules is that I think about an arrow, right? Think about an arrow, like a bow and arrow, that has little fletched, little things like this, right? They've got little feathers on the back, right? If the arrow's coming towards you and your eyeballs are right here, right? What you're going to see is the point of the arrow, right? If your eyeballs are over here and you're looking at the arrow going away, you're going to see the feathers of the arrow, right? So if it's going away from you, the arrow is into the screen. If it's coming towards you and you see the head of the arrow's coming. Does that make sense? That's kind of where that notation comes from, or how I remember it at least. Does that make any sense? Okay, so let's apply the right-hand rule, and you can see the right-hand. We can put both these on the screen at the same time, I think, right? There's the right-hand rule, and here's a problem. You're supposed to find the direction of the force on each one of these particles in this problem. Okay, so find direction of the magnetic force, F sub B, in each situation. And I'm going to give you guys a few minutes to do that. So we want to get an answer for A, for B, for C, and for D. What's the direction of the magnetic force in each case? I'll give you guys like 5 minutes. We'll start again at 4:47. So think about those. Talk to each other if you want to. What's the direction of the magnetic force in each case? You want to use the right-hand rule, and there's the right-hand rule. Take the time to read it. And yeah, I'm going to stand up, but I'm still here if you have questions. was about 4 minutes. I don't know if it was enough time. What did you guys get for the answer to part A? Okay, and I was going to say real quickly here, can you guys maybe just answer in the chat? That way people have more of a chance to answer at the same time. A is up. Let's see if I agree with that. Yeah, because you point the fingers of your hand kind of like this, right? I don't know how well I can do this, but your fingers would be like this. Is that what a right hand looks like? And you'd swing from here to into the board, right? From this way, you'd swing that way, and then into the board, and your thumb would point up. So the answer is up. Okay, what about B? Notice that it's a negative particle. Hopefully that doesn't trick you too much. Can you guys answer the question for this one? You're saying out of screen. I think I agree. The right hand rule, you would point the palms of your hand kind of like up like this. And then you'd rotate upwards. And your thumb would point into the board, but the thing is that you have to flip it. Your thumb would be going that way. So you'd have to flip it. I didn't want you to answer all the questions, but I guess that's okay. This one's going to be out of the board. Or out of the screen, or whatever you want to call it. Which is the symbol, right? The dot. Out of the board. This one's going to be... What's this one going to be? C? 0? That's right, because it's pointing parallel, or anti-parallel in this case. And this one right here, this is up, this is to the right. You'd rotate from up to right. What do you get for part D? I think this one's going to be into the board. Or into screen. That's it. That's the right-hand rule. You may or may not have learned this in Physics 1A. I know I talked about it in Physics 1A, but that's where you learn about the cross product. And anyway, so that's pretty much all there is to it. One of you have changed your name to Calvin Liang Jr. That is very funny. All right, so does anyone have any questions about any of those? If you weren't able to get it, that's okay. I mean, didn't give you much time, and perhaps the way in which I'm presenting this isn't making it super obvious for you, but you know, let me know. Do you guys have any questions? No? Okay. So, that's magnetic force from a conceptual perspective. So the next thing would be to do like a numerical problem, so we can actually see how the numbers work out. This isn't particularly challenging, but it's good to look at the numbers too to get a good, full picture of what's going on. So let's look at paste. There it goes. So we have a beam of protons with a charge this is the fundamental electric charge. They move at a speed of 3 times 10 to the 5th meters per second through a uniform 2 Tesla magnet. Oh, here's the unit. I didn't even mention to you guys what the unit for magnetic field is, but I'll tell you what, it comes from this equation. So our equation stated basically that the magnitude of the magnetic field was effectively equal to Q V B times the sine of an angle, right? So we can use this to define what the magnetic field vector is, right? So the dimensions of the magnetic field vector should be the same as the dimensions of FB, okay, divided by Q, dimensions of that, and the dimensions of velocity too, right? So what's this going to be? FB is going to be in units of newtons, right? Q is in units of coulombs, and velocity is in units of meters per second. But coulombs per second, right? 1 coulomb divided by a second, what's that equal to? Yep, this is an amp. 1 amp of current. So this is usually written as newtons divided by amp meters, or meters times amps. And this is defined as 1 Tesla. Okay, so 1 Tesla, same as the name of the automobile, is equal to 1 Newton per amp meter. in fundamental units. Remember that the ampere is the fundamental unit of electric current or charge. And the symbol uses Tesla. So this is a 2 Tesla magnetic field. It's actually a very, very large magnetic field in terms of the magnetic, just to give you an idea of what, these things. The magnetic field of the Earth, okay, is on the order of about 10 to the negative 5 Teslas. It's about 10 microtesla, you might say. Super tiny, right? I don't know, it's micro. The magnetic fields of, let's say, something like an MRI machine, right? MRI, I don't know if you know this, it stands for magnetic resonance imaging, so it uses magnets. For an MRI machine, I think the size of the magnetic field might be closer to like 0.2 Tesla or something like that. So 2 Tesla is huge. This would be a very large magnet, okay? And individual magnets that you find around your house might have a magnetic field of, maybe 20 microtesla or something like this, okay? So in this problem, a beam of protons with that charge moves at 3 times 10 to the negative, 3 times 10 to the 5, almost a million meters per second, through a uniform 2 Tesla magnetic field directed along the positive z-axis. So here's our z direction, there's our velocity, and there's our charge, right? So what we know here is that the angle between the 2 vectors is 30 degrees. We know, obviously, what the size of the charge is. It's given right there. We know what the velocity is. So this is the velocity, this is the charge, and there's the magnetic field right there, right? So if I want to find the magnetic force, this is very, very easy to do. We just take the size of, you do Q, V, B, sine phi. Your charge is positive that, multiplied by velocity, which is multiplied by magnetic field, which is 2. And then times the sine of the angle, which in this case is 30 degrees. And that's going to be equal to, it's not going to be a very big force, right? But they are protons, so what I got out of this, and you guys can verify if you get the exact same thing. I get 4.8 times 10 to the negative 14 newtons. Any questions? What direction would it point? Look at the picture. What direction would it point? Down, right? Negative j hat, right? Make sense? Pretty easy, right? All right. Now, it looks like a tiny force, right? But if you consider this, the mass of a proton, you want to know what it is? How big is the mass of a proton? Is it like 10 kilograms? It's like 10 to the negative something, right? Do you guys know what it is? Close. It's negative 27 kilograms. It's about 1.67 or 1.7 times 10 to the negative 27 kilograms. What would the acceleration be for this particle? You would just take the force over the mass, right? So look how big this acceleration is going to be. It's going to be like 10 to the something. Big. I don't know. So if we take that force and we divide by the mass of a proton, you're going to get a force, gigantic force. The force here is going to be something like 2.9 times 10 to the 13. Oops. 10 to the 13 newtons. This would be something like, what, 29, teranewtons, I guess? Think about terabyte hard drive. This would be a teranewton force. Huge amount of force, right? Oh, it's not the force, sorry, the acceleration, my bad. What am I doing? So sorry. It's newtons over kilograms, right? So this is in meters per second squared. An extremely high acceleration, right? What's that going to do to the velocity of this particle? Is it going to increase the velocity?
Yeah.
You sure? What direction is the force?
Down.
Is it pointing in the same direction as the velocity?
No.
Well, how are they related to each other?
They're perpendicular.
Yep. They're perpendicular, right? So is it going to increase the velocity? Why won't it let me pick the black pen? Does it just not like the black pen? Let's pick the blue pen then. This is really weird. Oh, there it goes. So how are these oriented, right? You've got your velocity vector that points this way, right? And you got your force vector that points like this. And they're at right angles to each other, right? So I ask again, is this going to actually increase the velocity?
No.
Why not? What's it going to do to the velocity?
Change its direction.
Change the direction. That's exactly right. The effect of this force is going to be that it doesn't actually accelerate the particle. Well, it will accelerate it, but not in the sense of like speed up. So the magnetic force is not actually going to increase the velocity. It's only going to change the direction. I'm going to go even farther to say that the magnetic force cannot, it's not possible, increase the size of the velocity, so I'll say speed. It can't increase the speed. It can only change direction. It can only change the direction of the velocity, right? So consider the following scenario. Let's say that I have a magnetic field, okay, and it points into the board. And it's just everywhere uniform magnetic field. So we say there's a uniform, meaning constant, magnetic field. A uniform magnetic field into the screen, okay? So that's our B N. And now let's say I have a particle. And we'll use a positively charged particle. So take a positive particle right here. And I give it a velocity vector that points this way. What's the direction of the magnetic force on this object? Is it up or down? Up, yeah. So on this particle, we're going to feel a force that's this way. The effect of that is going to be that it's going to turn the motion of the particle. The particle's going this direction, but the velocity vector is going to get tilted up, right? And it's eventually going to be moving, like as a result of this, it's going to move kind of off to some point, like maybe here. And now what's going to happen to its velocity vector is it's going to be tilted up like this, right? What I'm going to do is I'm going to go until it gets to eventually it's going to be somewhere like right here, at which point its velocity vector is going to be pointing this way. Whoops. Like straight up, basically. Yeah, you figured it out very quickly. The path that this particle actually travels along is going to be like a circle. Because the velocity is perpendicular to the force, right? This leads to circular motion, right? It's just like, imagine that instead of the force right here, you replace it with a string, and you replace the Q with a ball. You can whirl a ball in a string because the tension on the cord points toward the center, right? It's a central force. You can replace this with the Earth, and you can replace the magnetic field with the sun. The same thing happens, right? The Earth's velocity vector points this way, but the force vector points toward the sun. So the Earth goes in a circle. Really, it goes in an ellipse, but it's pretty much a circular path, right? For this, it absolutely travels in a perfect circle if the velocity vector is perpendicular to the magnetic field. Because at every point in its path, the force vector is going to be pointing towards the center, always. right? Force goes this way. When the particle gets to the top up here, the velocity's this way. What direction is the force? Use your right-hand rule. You should be able to prove that the force is still inwards. You could think about it. If you're the particle, the force is always to my left. This is like the particle is driving on a circular exit, right? And it's turning to the left the entire time until it gets back around to the same position. This is like what NASCAR drivers do, right? They drive in circles over and over and over again, always turning left, turning left, turning left. This particle is this way, but then it gets turned to the left, and then it's going this way, and then it gets turned to the left, and just forces it to move basically in a circle. Does that make sense to you guys? It's kind of impressive in a way, if you think about it. It means that you can capture, right? You can capture a charged particle, and you can hold it inside of a magnetic field like this to be used later on if you want to. Does that make sense? Why would you need to do this? Why would you need to hold a particle in a magnetic field like this? Well, there's some particles that you can't store in normal systems, okay? So I'll give you an example of this. If I take a bottle, okay, and I pour normal particles into it, the bottle can hold it just fine. But suppose that I pour antimatter into here. Okay, what's antimatter? Antimatter is exactly like normal matter, except it has the opposite charge. So for the electron, there's something called the positron, which is the antimatter particle of the electron. If I were to fill this bottle with positrons, does anyone know what would happen? What happens when matter... They explode. Something like 99.9% of the mass energy of the matter and the mass energy of the antimatter annihilate each other, producing pure energy. It's one of the most efficient ways to convert mass into energy that we know about, and it makes it so that you can't really store antimatter inside of matter. Okay? Does that make sense to you guys? If you were to walk up and touch a piece of antimatter, you would be evaporated. You would completely destroy yourself, even a very tiny amount of it, even like a few grams of antimatter. If you could hold it in your hand somehow, which would be hard enough to do, it would destroy you. Okay?
So it has like a domino.
I don't know. Domino effect. What do you mean by that? Maybe.
I can't think of a way.
That's okay. But the point is that you cannot really store antimatter in a bottle like this. However, antimatter, if it's charged like a positron, you can store the antimatter in a field like this. You just keep the things rotating in circles forever, never touching the system that you're part of, just being held in place by magnets. Does that make sense? This is how we store antimatter. We store it inside of magnetic fields that keep it moving in circles like this, which is pretty powerful. The last thing I'm going to leave you with here, and we'll probably say more about this next time, is that since this particle is moving in the way that it's moving, we can say that that magnetic force is the only force acting on it, and so we can use Newton's second law. And because it's moving in circular motion, Newton's second law would say that the net force acting on this particle, pointing in that radial direction, would be the mass times the velocity squared divided by the radius. And so if we call the radius of the motion r right here, and we say that that magnetic force is the only thing that's actually producing this motion, we can replace the magnetic force on this side with QVB. That's what we learned, right? And one of these velocities cancels out right here, and we end up finding that there's a radius for the motion that's completely given by taking the charge multiplied by the magnetic field and then dividing by the mass of the particle times its velocity, basically by its momentum. Did I do that right? R is equal to, nope. I'm going too fast because I'm noticing the time, running out of time. The V is over here, the R is here, we have to move the QB down to the bottom. So R is going to be equal to the momentum of the particle, mv, divided by Q times B. This would be the radius of this motion here. It's given completely by the mass of the particle, the charge of the particle, the size of the velocity, and the magnetic field, right? You guys see that? Notice something else that shows up here. Imagine that you design a device where you force the particles to move at a certain radius, so you can measure the radius, right? And let's say you know the velocity of the particle through some other method, and you know the size of the magnetic field through some other method. You could actually use this to figure out what the mass over the charge ratio would be for your system. This was one of the first ways that people understood the charge to mass ratio for the electron. And unfortunately, there's a lab we would have done where you would calculate this, but we can't do it this semester, unfortunately. Anyway, it is pretty cool that we can do it. That contained within this idea is the ability to find the ratio between some fundamental quantities, such as the mass of an electron and the charge of an electron. And when you compare this to another experiment called the Millikan experiment, taken together, you can use this to find individually what the mass of an electron is and what the charge of an electron is. That was kind of the beginning of particle physics, which is what I studied in college. And it kind of starts from here. The connection between magnetism and charges in motion. Okay, I think that's all I have for you guys today. Do you guys have any questions? We'll pick it up from here next time. We'll do some problems discussing how we can use this relationship right here. And we'll also discuss applications of this, what a mass spectrometer is, what a velocity selector is, and all that kind of stuff. And that is it for today's class.